This video is an introduction to quantum mechanics, and although it doesn't necessarily follow the historical progression of the content, I think it is presented in a way that will go from no understanding of quantum mechanics to some useful understanding for general chemistry students. So we're going to start our discussion looking at blackbody radiation. So at the turn of the previous century, the end of the 1800s, physicists had pretty much closed the book on physics. They thought that they knew pretty much everything there was to know, and they thought that all that was left to do was to know what was known to a greater level of precision. So essentially just to add decimal places to values that were known. But there was a couple of outlying problems that were still to be solved, and one of those famously was blackbody radiation. So what's a blackbody? A blackbody is any object that can absorb and emit electromagnetic radiation unimpeded. So essentially can absorb any frequency of energy, can emit any frequency of energy. To give you a physical example or a visual of a blackbody, imagine a horseshoe or a metal object that you've heated so it's red hot. That redness, or that what you would see to notice from a distance that that object is emitting energy, that would be a blackbody radiation. Okay, so on this visual here, we've got intensity. I've symbolized rho. The intensity, which is a factor of temperature or temperature dependent, and is related to frequency, nu, is plotted on the y-axis against wavelength, lambda, on the x-axis. The solid line that you see here is the experimental data. So we can see that black bodies, as they emit shorter wavelength light, the intensity increases, and then suddenly it starts to decrease. So this is what is seen experimentally. What was theorized, though, based on classical mechanics, is the dash line. So at high wavelength, and we should say that here the energy is proportional to 1 over the wavelength. So at high wavelength or low energy, classical mechanics, or the equations of classical mechanics, pretty much account for blackbody radiation. Problems quickly arise, though, as the energy starts to increase. The equations theoretically predict a runaway intensity of radiation, which starts to increase exponentially and doesn't it doesn't tell the story of the world we live in. It would suggest that objects that emit blackbody radiation do so with a runaway effect on energy, and so everyday objects would emit massive amounts of radiation, and that's certainly not what we see in the real world. So there's a problem. Our theory doesn't predict reality, and so our theory has to be readdressed. So just to pinpoint, because of this, this is the low energy, and this is the high energy. Okay. So the classical theory, again, predicts this runaway so classical theory predicts this runaway increased intensity of radiation. And because this is bad, it's catastrophically bad, and it's high energy, the first type of high energy that seems to be bad for humans is ultraviolet energy. So it's known as the ultraviolet catastrophe. So you should know the buzzword ultraviolet catastrophe or UV catastrophe. It's linked to, so when you hear the word ultraviolet catastrophe, I want you to know that it's essentially what happens when you try and use classical physics, classical mechanics, continuous energy mechanics, to try and explain blackbody radiation. Something bad happens. So let's look in a bit more detail what the classical theory says. So the classical theory, and when I say classical, I just mean continuous energy. Essentially says that this function, so we'll call it rho, so this function here, the intensity, we'll call it rho. It's a function of temperature, but it impacts frequency. And it's equal to the number 8, the number pi, K, which is Boltzmann's constant, T, which is temperature in Kelvin, frequency squared, divided by speed of light cubed. So that's what classical theory says on the assumption that energy is continuous. So the intensity of the radiation from a black body, the intensity of black body radiation, is the constants 8 pi over c cubed, where c is just light speed, which is a constant, and then Boltzmann's constant by temperature times by frequency squared. We probably should point out that kT is classical energy. Or again, K is Boltzmann's constant. We've seen kT before. You typically bump into it when you look at ideal gases. Okay, so that's the setup. Now, so again, this is around the end of the 1800s. Around 1901, German physicist called Max Planck. So again, around the turn of the 20th century, which means about 1901. So about 120 years ago, Max Planck suggested that energy can no longer be considered to be continuous. That energy cannot be continuous. Energy cannot be continuous. Why is that a reasonable assumption? Well, the other option is if it is continuous, disaster happens. So the opposite of disaster is probably where I'd bet my money. So what's the alternative then? Well, instead of continuous energy, he suggested that energy comes in packets. Packets of energy, packets are quanta, packets, pieces, quantities, quanta, all mean the same thing. And each packet of energy has a probability of being available. Being available or being activated. Okay, so we're going to state the equation, and then we will erase the board, and then we'll come back and look at what the equation means and why we should have some kind of trust in it. So the equation that he offered was that the intensity, so this same function, the intensity of the blackbody radiation, which is a function of temperature and it depends on frequency, is 8 pi h nu cubed, where h now, instead of Boltzmann's constant, we have Planck's constant, h, all over c cubed, all over c cubed. So far, all Planck is suggesting is that we replace Boltzmann's constant with Planck's constant. And notice we've increased one factor of frequency here. We've got frequency squared, and now we've got frequency cubed. But then there's a probability component. Now, this probability component in what was later to become quantum mechanics is vital. So this probability term is 1 over e to the h nu divided by kt minus 1. So this term here is the probability term that we mentioned earlier. So other than that, there's a subtle change to the original term. And this is what was offered by Max Planck. And this was going to be the quantum concept of energy, so discrete energy. So quantum, which means discrete. So again, in comparison with the classical continuous energy, this was the quantum discrete energy. So in comparison with kT, which is our classical energy, we have this concept of h nu. So the extra nu that we added was from h nu. So h nu, this is now our quantum energy. Okay, so we've swapped out the constant and we've got an extra factor of nu. That's because of the introduction of h nu. And essentially, Planck assumed that energy can come in multiples n, where n is just a number, of h nu. And n itself can be any number. It could be 1, it could be 2, it could be 3, etc., all the way to n. So it can be any whole number, a whole discrete number, but it can't be fractions of numbers. Okay, so this is what Planck said. Why should we believe it? Well, let's erase this board and we'll see why we should believe it. So I'll erase this board carefully so it doesn't fall on the floor. I figured out a way not to kneel down now, so I've got my whiteboard suspended on chairs. Okay, so that's why I have to be careful it doesn't fall. Okay, so why should we have any confidence that this is a right approach to solving this type of argument? Well, essentially, he's basically saying, especially with this probability concept, he's saying that when atoms vibrate, they release energy. And he's basically saying that there comes a point at which it gets harder and harder, and it's less likely that they'll vibrate with a very high frequency or a very high energy. So let's see some of the arguments he said. So he said at sufficiently high temperatures, all oscillators would probably be excited, and hence the new quantum energy should produce the classical result. So let's write it here. I'm going to call it Planck's thinking. So Max Planck's thinking. At sufficiently high temperatures, all oscillators. An oscillator is just, in this case, it's just an atom that can absorb energy and oscillate, or release energy by changing its oscillation frequency. So here the oscillator is just an atom in the black body, a constituent of the black body that allows the absorption or emission of energy. Okay, so at sufficiently high temperatures, all oscillators would probably be oscillating or be excited. So here's this word of probable again. So this probability introduction that Planck had. So probably be excited. That just means they would be oscillating. And hence the new quantum energy should produce the classical result. So Planck's thinking, at sufficiently high temperatures, all of the oscillators, the atoms that are vibrating, would probably be excited, they would probably be oscillating, and hence the new quantum energy should produce the classical result. Okay, so this is our litmus test, see if this kind of makes sense. Okay, so that was his thinking. Just in terms of space, now we've looked at the thinking, I'm going to erase the thinking so I can actually fit the equation on the board. So let's go ahead, erase the thinking. We'll actually put the equation on the board. Actually, I'll probably get rid of this as well, so we can get everything done on one board. Okay. Okay. So consider this factor here, h nu over kt, which was in Planck's new equation. So it's essentially the quantum idea of energy over the classical idea of energy, Planck's constant by frequency over Boltzmann's constant by temperature. Well, this factor should tend to 0 in magnitude, since temperature is tending to infinity. Or rather than since, we could say when, I guess. Okay. Sorry, if you can hear a 3-year-old shouting, my wife's homeschooling it in the next room. So sorry about that. H nu over kT tends to 0 when temperature tends to infinity. Again, we're looking at sufficiently high temperatures to excite all oscillations. All the oscillators are moving. We should see a continuous energy result and regain the classical outcome. We're going to use a mathematical tool here. E to the power x is approximately 1 plus x for small x. So we're going to use that tool to simplify our equation in a second. So e to the exponent x is approximately 1 plus x, so long as x is small, close to 0. So then we can look at our equation. So thus, we've got our rho t as a function of nu, our intensity of blackbody radiation, is 8 pi h nu cubed over c cubed, and then the probability part of the equation, 1 over e to the h nu over kt minus 1. Okay. Well, this is approximately 8 pi h nu cubed over c cubed. So we've got our original one here. Now we're going to look at the probability. Okay. So we're going to use this. So we've got E, let this be X. So we've got 1 plus this material according to our expansion here. So it's 1 divided by 1 plus H nu over KT minus 1. Okay. So the E to the X just becomes 1 plus X. So e to the h nu over kt becomes 1 plus h nu over kt. And then we have minus 1, so we have minus 1. We've got plus 1 and minus 1, so that cancels. And then we've got 1 over h nu over kt. So the kt wraps around as a numerator because it's currently a double denominator. So in short, we've got ht nu is 8 pi h nu cubed over c cubed, and then we've got a factor of kt over h nu from here. Kt wraps up, we've still got h nu. Planck's constant cancels Planck's constant, and the nu cancels one of those. So we're left with 8 pi kt nu squared over c cubed, which you'll recognize as the original classical result. So again, our hypothesis was at sufficiently high temperatures, all of the oscillators would probably be excited, so the new Planck equation would be expected to reproduce the classical result. We tried it, and indeed, that's what happened. We generate the classical result again. Note at this point then, and this is something good in any, just good way to think about development of any theory, Planck's idea of discrete packets of energy. So Planck's idea of discrete packets, remember packets are just quanta, of energy, they didn't just replace classical mechanics, they built on it. They built on existing classical theories. Quantum idea built on classical idea. Why didn't people do this before? They didn't realize they had to. It was only the realization that something was wrong was when they couldn't explain brand new phenomena. So like with any theory is only as good as the phenomena it explains. You have to keep trying to explain, be observant of new phenomena to see if your current theories explain them. Okay, so next we will... There was another experiment that also was causing people some problems trying to explain. So we'll move forward a couple of years now to a contemporary of Max Planck, Albert Einstein, who was able to explain the photoelectric effect. So let's have a look at the photoelectric effect. Carefully erase the board so I don't collapse the whole thing. Okay. Okay, the photoelectric effect. About 1905, and we associate the triumph of this explanation, we associate with Albert Einstein. So the photoelectric effect, photo means light, electric means electron, and effect means there's some interaction between light and electrons, essentially the forerunner of the modern photovoltaic cell. So light was able to eject electrons from metal objects, and essentially the movement of this movement of electrons from metal objects could generate electricity. So we have this forerunner of the modern photovoltaic cell, or solar panel, if you like. Okay. So the basic concept is, if you take a metal surface, take a metal surface, let this line represent the surface atoms in a piece of metal. Then we have light coming in, so a light wave here. And then under certain conditions, an electron could be ejected. So light comes in, an electron is ejected. So Einstein embraced Planck's idea of discrete energy to help explain this, and so therefore the triumph of this explanation further supported the concept that energy is discrete and not continuous. So let's take a quantum of light. So Planck told us that light is proportional to frequency. So it's the frequency component that's important, and there's actually a threshold frequency beyond which the light would have to exist at in order to eject the electron. Okay. So Einstein was able to produce the following equation. So Einstein's interpretation essentially is that energy, so the energy of the light, so let's call it E here. So the energy that comes in, here I've just called N1, so we just have one photon. The energy that comes in, it has to do a couple of things. It has to give kinetic energy to the electron. So there's a kinetic energy component. But it also has to break whatever forces were keeping the electron in the metal itself. So if you imagine that the electron is in the atom because of interactions between the electron and the nucleus, we have to break those interactions. We have to ionize the atom. So the energy that comes in has to do work to pull the electron out of the atom, and we call this the work function. We call this the work function. So the energy of the light, in order for this to be a successful process, the energy is now converted because of conservation of energy. You can't create or destroy energy. It's converted to the sum of the kinetic energy of the ejected electron, plus some is lost as the work function needed to rip this electron out prior to moving it with kinetic energy. Okay. If we plot energy, remember energy is kinetic energy plus the work function. The symbol, if you're interested in what this symbol is, it's just phi. So let's call it PHI. So phi. Okay, so if we plot energy on the y-axis against frequency on the x-axis, we get a straight line where E is h nu. E is not h nu. Well, E is h nu, but that's not here. So I need to change my notes. Okay, so this is just a y is mx plus b equation. So it's a straight line equation. What would the slope be? So we know that m is the slope. So if we go back to our high school days where the slope is the rise over run. So the slope is the rise is energy, the run is frequency. So we know that the slope is just Planck's constant. So this is a way to quantify Planck's constant. Again, because we know energy is h nu, so therefore energy over nu is h. So we're able to quantify Planck's constant. Okay, we're able to quantify Planck's constant. Let me just tweak that note. Okay. Okay, so we've got nice y is mx plus b. We've quantified Planck's constant. And just to give you an idea of what this might look like, I don't know, I think this diagram might be useful. Let's see. We have what's called an electron sea here. So an electron sea, or a reservoir of electrons, because this is in a metal. If we have this axis here is energy, which is kinetic energy plus the work function. Okay. The work function would be this component here. The kinetic energy would be this component. So essentially the energy paid, so who pays the tab? Who pays the energy tab? The energy is paid by the light. So how do you know you have enough energy light? The light has enough energy to eject an electron if it's able to get an electron out of the electron sea and give it kinetic energy. So it at least has to broach the work function threshold, and then it can have a variety of kinetic energy, so it could be down here. If it's up here, it ejects faster. So I guess this would be the threshold. But this is the energy tab that's paid for by the quanta of energy, the quanta of light. Okay, we'll erase this board. We're about 37 minutes in, so I'll try and keep this around an hour and then just carry on with the second video if needed. But let's plug some numbers in and actually do a calculation on the photoelectric effect. Alright, so I'll erase the board. So for the purposes of history, it's March 21st today, it's a Sunday. I'm making this video for my general chemistry students because we're all socially distancing ourselves because of the COVID-19 outbreak. Okay, and this video is being broadcast from Huntington Beach, California. Okay. So question, let's call it question 1. So the work function for cesium is 2.14 electron volts. Electron volt is just a unit of energy. We can convert it to joule. The work function for cesium is that value. Calculate the kinetic energy and the speed of any ejected electrons by A light of lambda equals 750 nanometer and B light of lambda equals 250 nanometer. Okay. Let's do A first. Well, we know that from Einstein's equation, we know that energy is kinetic energy plus the work function. Fine. If we want to solve for kinetic energy, we can just transpose the work function over here. So kinetic energy is the energy of the incoming photon of light minus phi. There's another equation that I'm going to need. Energy is hc over lambda, where energy is the energy of the photon, h is Planck's constant, c is light speed, and lambda is the wavelength of light. I'm going to plug my values in here, so I know that E is 6.63 by 10 to the negative 34 joule seconds. So that's a numerical value of Planck's constant. It's very small, has units of joule second. Light speed is 3.00 by 10 to the 8 meter per second. It's very, very large. And lambda, we need lambda in units of meter to cancel this meter over here, but it's given to us in nanometer. So we're going to have to do a little conversion. 750 nanometer is our input, and I know that 1 meter is 1 by 10 to the 9 nanometer. So I can cancel my nanometer here and here. My meter now cancels here. My second cancels reciprocal second. And I'm going to be left with energy in joules. Okay, which gives me 2.652 by 10 to the negative 19 joules. If I was being very particular about significant figures, which I'm not, to be honest, then I would probably interpret 750 as being 2 sig figs, so this would limit my calculation to 2 sig figs. To be honest, I'm not really that concerned about sig figs here. The bigger picture is the photoelectric effect, so we'll just focus on that. Okay, so we have a very small number of joules. Let's now calculate the kinetic energy. Now that we have the energy, let's use it to calculate the kinetic energy. We've been given the work function in electron volts, so we're going to have to convert electron volts to joule, or we'd have to convert our joule into electron volts. But because we're going to take a difference, we just have to make sure the unit's the same. Doesn't matter which unit. Because joule is much more common in chemistry, we'll convert electron volts to joules. Okay, so kinetic energy is our energy, so we're looking at this equation here. Kinetic energy is our energy, which is 2.652 by 10 to the negative 19 joules, minus, and now I've got my 2.14 electron volts, but I need to convert that to joule. So I use the conversion. 1 electron volt is the charge on the electron in units of joules. So the charge on the electron is 1.602 by 10 to the negative 19 joules. And that's 1 electron volt. Okay. So electron volt cancels electron volt, and now I've got joule minus a number of joules. This gives me a negative value, and it's 7.8 by 10 to the negative 20 joules. So here I've rounded to my 2 sig figs. 7.8 by 10 to the negative 20. Importantly, there's a negative value. So we'd have to physically interpret what that means. This is a negative kinetic energy. Now this is a velocity. So rather than having a velocity, rather than there's a velocity component to kinetic energy. So kinetic energy is positive. The only way it can be negative is if the velocity component is in the opposite direction. So our physical interpretation of that negative is that there's no ejection. So this is a failed photoelectric event. Providing photons of light at that wavelength is too low an energy. It hasn't overcome the threshold needed to eject the electron. We'll erase this. We'll look at example B and see if we fare any better with B. So this is our answer to part B. Same idea now. So we've got E is hc over lambda, which is 6.63 by 10 to the negative 34 joule seconds. That's Planck's constant. By light speed, 3.00 by 10 to the 8 meter per second, divided by 250 nanometer. So remember, wavelength is proportional to 1 over energy. So a smaller wavelength should give a larger energy. So is it large enough? We will see. 1 meter is 1 by 10 to the 9 nanometer. Our nanometer cancels. Our meter cancels. Second and a reciprocal second cancel. So we've just got energy in joules. And this is 7.956 by 10 to the negative 19 joules. Kinetic energy is therefore 7.956 by 10 to the negative 19 joules. Minus, we're going to do the same again. We're going to convert the work function from electron volts to joules. So we've got the charge on the electron in units of joules, and that's equal to 1 electron volt. Electron volt cancels here and here. So we've just got joule minus joule, and then we're going to round the answer to 2 sig figs. And this gives us a positive value, and it's 4.5 by 10 to the negative 19 joules. We interpret this positive value as an actual ejection. So this is a successful attempt to eject the electron. This lower wavelength photon was above the threshold, needed to broach the work function, and had excess energy needed to liberate and give some kinetic energy to the electron. Let's now go and calculate the velocity. So now we know that we actually have a velocity to calculate. We can go ahead and calculate the velocity. Well, we know that kinetic energy is mv squared over 2. So kinetic energy of the electron is its mass, its square velocity over the number 2. So we know that v squared is twice the kinetic energy divided by its mass. And then we know that v, the velocity itself, is just twice the kinetic energy over its mass, and the whole thing is square rooted. So we can calculate the velocity. Velocity is twice by the kinetic energy, which is 4.5 by 10 to the negative 19. Now joule, we're actually going to interpret what joule means. We're going to use the fact that joule is a kilogram meter squared per second squared. So we're actually going to use this, and rather than write joule here, we're going to write kilogram meter squared per second squared, because when I square root meter squared per second squared, I'm going to get meter per second, which is the unit I need for velocity. Okay, so joule is kilogram meter squared per second squared. Okay, so twice the kinetic energy divided by the mass. The mass of the electron is 9.109 by 10 to the negative 31 kilogram. And now I need to take the square root of this whole thing, so we raise it to the half power. That's the square root. And it gives us about 10 by 10 to the 5 meter per second. So it's less than light speed, so that's good, because it can't be greater than light speed because we have a mass. But it's definitely fast. So we have some kind of feel for the velocity of a successfully ejected electron, and we know that there's an energy dependence on the viability of actually ejecting an electron. Okay, so this will basically lead to the end of this video. So just to sum up what we've looked at in this video, sit down again. What we've looked at in this video is we've started to look at some quantum mechanical ideas. From an historical point of view, we've seen rumblings in the late 1800s that would suggest that not everything could be explained by classical mechanics, and by classical mechanics we mean a continuous amount of energy. The Blackbody experiment, the Blackbody radiation experiment, is pivotally couldn't be explained. It led to, when it was interpreted by classical mechanics, it led to a catastrophic increase in the intensity of radiation emitted by a blackbody at relatively low temperatures, which would suggest that even at room temperature, every surface in a room would be ejecting enough radiation to kill everyone in the room. So clearly that wasn't the case. That's not what we observe when we go into a room, even in COVID-19 world. Historically, I don't know what was going on in Planck's head. Retrospectively, we can interpret what he must have been thinking is, okay, well, continuous is just off the table. Continuous energy is off the table. It obviously doesn't work. What's the opposite of continuous? Let's give that a go. So that's how I personally view it. The opposite of continuous is discrete. I need to put the brakes on any frequency of energy being available. So let's put gaps. Let's make the allowed energy come in packets with gaps in between those packets. So that must have been, that's the only logical way he could have come to that argument. And then trying to incorporate that argument into the mathematics in a way that would regenerate the classical result, which had to be modeled under classical conditions. We showed that that was the case. But there's this introduction of a probability, and this is a theme that we'll come back to. And then Einstein's use of this quantized version of energy, this quantum mechanics, to explain why only certain frequencies of light were able to eject electrons from metal surfaces in the photoelectric effect. So rather than light being proportional to its amplitude, high intensity, low frequency, just simply changing the amplitude of the light was insufficient to change the outcome of the photoelectric effect. But changing the frequency of even low intensity light above the threshold of the work function was enough to eject an electron. So neither experiment could be explained by classical mechanics. Both experiments could be explained by quantum mechanics, hence mounting evidence supporting the acceptance of quantum mechanics. And that concludes this video.